Hello, I'm Dr. Paris von Lockett, and today I'll be talking to you about weldments in SolidWorks, or weldment profiles. Weldment profiles are a way in SolidWorks that you can design the cross-section of a frame structure. That allows us to have an arbitrary cross-section. They have some built-in ones, and then that frame structure can be made up of multiply connected beams with those cross-sections. So we can get at how we design those structures in SolidWorks. It's a pretty involved process, but there's a long tutorial that will help you step through it. Okay, so the slides and video for today focus on some practical hands-on applications of SolidWorks. As I said, the main topic of this lecture right here is weldment profiles, an overview, kind of high level of where they fit within the SolidWorks hierarchy and how you go about beginning to implement them. Also important is the direction of shear and moment within your weldment profile, because the direction that you define that profile in will affect the shear and the moment diagrams based on the directions of the forces and the moments within that beam itself. So you have to have those things all aligned. Additional topics for today's lectures that you should look for on Canvas include a review of geometric relationships in SolidWorks. It's good to have a strong understanding of this because as with any CAD package, and especially within SolidWorks, there are relationships between all your geometric entities, and so if you change one, you'll change another, and that allows us to do some parametric design in SolidWorks, but also can help us out with some parametric analysis in our simulation side as well. We'll also be resolving the beam problem, resolving the beam problem from the last FEA lecture. That's a video posted by Dr. Kraft, a tutorial on weldments that will run through that problem and show you some tips and tricks, and also show you how to try and compare your results. So be sure to check out those 2 additional lectures at the bottom. So SolidWorks, the weldment profile tools can be used to define frame structures, which are beams. The beams then are multiply connected to each other, and each beam can have a different cross-section. And this weldment profile tool allows you to make those cross-sections. It links them together as single parts, which is helpful for analysis and helpful for some other things that we'll talk about a little bit later. So the weldment tool allows you then to create these what are called structural members. As you remember from solid mechanics, we can have beams, we can have trusses. Beams allow you to transmit both forces in X and Y and moments, whereas axially loaded trusses only allow you to transmit forces along the direction of the truss element itself. You can't transmit, what do I call it? You can't transmit moments. So there's a big difference between frames and trusses. We'll be focusing on frames for this class, largely because that's kind of more the realistic application side. Rarely do you see an actual truss structure in an engineering application, I guess, as opposed to frames, because the joints are often either welded or bolted together. So this weldment profile, like I said, defines the cross-section of the beam. You can get into this by looking through SolidWorks tools, options, file locations, weldment profiles, and within that, SolidWorks actually points to a specific location on the hard drive listed here. That's going to be important in the tutorial because when you're defining your own weldment profile, SolidWorks actually needs it to be in a specific directory. And it's somewhat convoluted to actually do that, but the tutorial steps you through on actually how to go about it. So pay some pretty close attention to that. Where those files end up is important. The tutorial, like I said, will step you through it and show you how to make it. SolidWorks also, however, does allow you to pick from a short list of available profiles and sizes, but if we're dealing with a CAD program and we want to actually do our own design to fit our needs, then maybe we want something that's more suited to our task. And so arbitrarily profiles can be an improvement, and so that's why we're showing you how to do them. As you look below, figure 1, it shows a short list of profiles, either from ANSI, A-N-S-I, or ISO, styles and sizes. We'll talk about what those mean in a second, but essentially those are agencies that have been developed to create standards for various technical applications. Before we get into the definition of ANSI and ISO, however, it's important to remember that within the definition of a profile, we have to define its dimensions, and we have to define those dimensions such that we understand if we have some sort of transverse load here going possibly in our one direction, as you might expect from the I-beam on the left or the cross-section on the right, that's the direction of interest for our shear and our transverse loading. Because of that, when we define our profile, we have to make sure that we define that long dimension as our one dimension, such that when we then go to look at shear and moment diagrams, especially the shear diagram, we pick the correct direction with respect to our profile. So understand that these definitions within the profile are with respect to the profile. They are not necessarily with respect to the world axes. And so we have to understand when we apply that profile to a beam that we're using in our model, we know what direction the one is, such that we can then go back and find the correct shear diagram. To create a moment diagram about the z-axis, then, we would use direction 2. As you can imagine, from a right-hand rule, you can see that that cuts through our neutral axis, and so that's the direction for our moment. So our 2-axis is important as well, and like I said, we have to keep up with both of those when we're looking to apply our loads and then to look at the results of our analyses to make sure that we're getting shear and moment diagrams from the correct directions. All right, back to ANSI and ISO. These two organizations develop standards to improve technical communication, which in turn is directed at improving the manufacturing processes and reduce errors and remove guesswork from CAD designs and translating those things into physical parts. ANSI stands for the American National Standards Institute. That's the primary organization in America for developing technical standards. It also works with groups overseas, specifically the International Organization of Standardization, ISO, and the International Electrotechnical Commission, IEC, to normalize these standards globally, at least as much as possible. And if you've worked with this, you've probably seen some of the differences between ANSI, ANSI, and ISO. With respect to what we're dealing with, it's going to refer to a style of annotations, objects, lines, hidden hatches, cutting planes, and how we define those things in tolerancing, how we define those things within a CAD drawing such that there's a uniform understanding when anyone looks at the CAD drawing, they know what all the symbols mean, and more importantly, they know the relationship between all the entities on the page. So hopefully either from 340 or from eDesign 100 or another class, you've gotten familiar with geometric dimensioning and tolerancing, or GD&T as it's called. This is really important to establish uniform practices for how we actually communicate this information and communicating what's called design intent. What do we mean by that? So what this means is that the technical drawings have the desired form, fit, and function, and interchangeability when we actually develop parts from them. So we want to make sure that whatever we put on the page gets across the complete intent of the part, and that part, once produced, will actually have be able to work in the environment for which it was designed. And ultimately, the goal is to improve quality, to lower costs, shorten delivery times, just to remove errors in translating CAD drawings into physical parts, and also to remove the sort of interpretation that comes along with it and the back and forth and question asking that might go along with it if things aren't as clear as they could be. All right, so that's all I have for you in this particular lecture. One of the next lectures you should pick up that's the most important for today is the Weldments tutorial designed by Dr. Ruben Kraft. Here it's shown on the right, beam analysis using weldment profiles. So he came up with this as a way to teach you guys how to actually employ weldments, how to design your own profiles, how to make sure that they're working within the SolidWorks environment. And if we can do that, then you can employ an arbitrary profile, which is actually required for the homework. So make sure you pick up this lecture, make sure you work through this tutorial. There is an application packet, a technical document online to go along with the video that he's produced. And like I said, this will resolve the problem that you worked by hand from the previous lecture on beam problems, that example problem. So if you haven't done that example problem, please go back, do that first, get familiar with it, get familiar with the solution and how we eventually generate shear and moment diagrams, because that's the ultimate goal for the tutorial as well. All right, well, thank you very much for participating. Thanks for watching. Hopefully you have a little bit of background on where weldments fit within SolidWorks, how weldments are used to design frames and frame structures and their importance within engineering design. As I said, make sure you pick up that tutorial, work through it, and you'll become a master of making frame designs. And after that, we can move on to bigger and better things in later lectures with more of the SolidWorks tool and more of its functionality.